In order to establish the analysis, we will set up a few definitions. Okay. So, we are interested in RG center based recombination generation mechanisms. So, the first definition is, let us say that the electron concentration, the free electron concentration is n, okay, and the whole concentration is p, and therefore, dN by dt due to RG mechanisms is given by the time derivative here, and the rate of change of the whole concentration due to RG mechanisms alone is given by the rate term here. Now, we are only looking at RG center based recombination generation. So, let us say at energy level E t we have a certain density of states, density of trap states, and let us say that the total number of trap states per unit volume is given by capital N T. Okay. So, that is the total number of trap states per unit volume, that is the trap concentration. Now, of this capital N T, some of the traps are occupied by electrons and some of the traps are empty. The traps that are occupied by electrons, we will say that it has got a concentration of small n t. Okay. So, these are traps that are occupied by electrons, it is the number of traps per unit volume located at E t that are occupied by electrons, and the number of empty states, or you can say that the empty traps or traps that are occupied by holes are P t. Okay. So, there are P t traps per unit volume that are empty, and since N t and P t have to sum to capital N t, we have a fixed condition here wherein capital N t is a constant, whereas N t and P t are more dynamic. Okay. So, small n t and P t, these counts could change with time. Okay. So, for example, if you are not in steady state, these concentrations could change in time, but the sum of these two cannot change the time, capital N t is fixed. Okay. So, these are our little definitions, and we will use these definitions to define the dynamics of RG mechanisms. So, what is the rate of change of electrons due to RG processes? Any change would depend upon the rate at which electrons are emitted minus the rate at which the electrons are captured. Okay. So, you have your conduction band edge, you have your valence band edge, and you have some trap states here. Some of these trap states are occupied by electrons, and you have some free electrons there. Now, what is the rate at which electrons are emitted? The rate at which electrons are emitted, the emission can only happen from the trap states. Okay. We are not talking about band to band generation here. So, emission implies generation. So, by this we actually imply generation. Okay. And we use the word emitted because these electrons are going to be generated from the trap states, which is equivalent to saying that the electrons are emitted from the trap states. So, what is the rate at which the electrons are emitted? They depend upon the number of electrons present in the trap states. If none of the trap states have any electrons, the rate at which electrons are emitted is 0, because there are no electrons to be emitted. Okay. Therefore, it is only when the electrons are present in these trap states that an emission is possible, and therefore, the rate at which electrons are emitted is proportional to N t, because N t is the concentration of trap states that are filled with electrons. And we will define a proportionality constant called E n, which is to say the emission of N type or the emission of electrons, and say that the rate of electron emission is equal to E n into N t. Now, what is the rate at which electrons are captured? The electron capture involves a process wherein the electron that is sitting in the conduction band and which was free is now going to be captured by a trap state. Okay. So, there is an empty state here and this free electron is going to drop down and it is going to occupy this empty state. So, that is the capture of an electron. So, what does that mean? What does that depend upon? Firstly, it has to depend upon the number of electrons or the concentration of electrons in the conduction band. If there are no electrons in the conduction band, then the rate of electron capture is 0 because there are no electrons to be captured. So, definitely the rate of electron capture has to be proportional to n. So, let us say there are electrons to be captured. What else is it proportional to? These electrons can be captured and for them to be captured they need to find an empty state. Okay. If there are no empty states at ET, the electron cannot be captured because there is no state for the electron to occupy. So, remember the states are nothing but solutions to Schrodinger's equation. So, you need to have two conditions. You need to have electrons that are there to be captured and you need to have empty states for these captured electrons to occupy. So, it is only when you have these two together that you can have a rate of electron capture. So, therefore, the rate of electron capture is proportional to n and it is also proportional to the concentration of empty states and therefore, it is proportional to Pt into n, where Pt is the concentration of empty states or the number of empty states per unit volume located at ET. So, the rate of electron capture can be defined to be equal to Cn Ptn, where this term Cn is a proportionality constant which relates to capture of electrons. Okay, so, we have defined two constants of proportionality En and Cn. So, now let us talk about the holes. Just like in the case of electrons, what is the rate of change of the hole population? The hole population depends upon the rate at which the holes are emitted from the trap states and the rate at which the holes are captured into the trap states. Just like in the case of electrons, so all these empty states are essentially holes, right. So, just like in the case of electrons, the rate of hole emission, so I am sorry this is a typo, this should be holes, the rate of hole emission, okay, has to be proportional to Pt, because if there are no holes in these states and if all these states are filled with electrons, there can be no holes emitted. So, it is only when you have holes located in these states that you can have an emission of a hole to the valence band. So, therefore, the rate of hole emission is equal to Ep into Pt, where Ep is again another proportionality constant relating to the emission of holes. And the rate of hole capture by the same arguments we used for electrons is proportional to Nt into P, with Cp being a constant of proportionality which is the capture of holes. Okay. So, we now have 4 rates: the rate at which electrons are generated and the rate at which electrons are captured, the rate at which holes are emitted and the rate at which holes are captured. So, based on that we can set up 2 neat differential equations, okay, one pertaining to the electrons and one pertaining to the holes. And this basically tells you that the rate at which the electron population changes because of RG mechanisms. So, remember we are not talking about the total. So, if you go back a few slides, this is the total change of the electron population in any given volume. We are only talking about the RG mechanisms. Okay. So, the rate at which the electron and hole count changes because of RG mechanisms is the rate at which electrons are emitted minus the rate at which electrons are captured, and the rate at which holes are affected due to RG processes is due to the rate at which is dependent upon the rate at which holes are emitted minus the rate at which holes are captured. So, So, this is our starting point for any analysis. So, at non-equilibrium, okay, so we are now out of equilibrium because we are having a lot of dynamics and there is generation and recombination mechanisms going on. At non-equilibrium we have been using these variables En for the proportionality constant determining the emission of electrons, Cn for the capture of electrons, Ep for the emission of holes, Cp for the capture of holes, Nt which is for the number of occupied trap states, Pt for the number of unoccupied trap states and all per unit volume, N for the free electron concentration and P for the hole concentration. Now, this is at non-equilibrium. Now, at equilibrium denote these variables, okay, with a special symbol, okay, and we want to say that at equilibrium these values have got a special value which is given by the subscript O attached to all these parameters. So, at equilibrium all these parameters take these values, okay, and this is a special condition because everything is at equilibrium. Now, why do we want to consider equilibrium condition? Because we can make a lot of calculations at equilibrium conditions. We can easily calculate electron and hole counts at equilibrium, and we want to take advantage of that to see what happens when we push the material slightly out of equilibrium and into the non-equilibrium condition. So, at equilibrium you have dN by dt Rg has to be equal to 0, okay, because everything is balanced out. So, which means that if you go back to these two equations and you rename or change these variables to their equilibrium values. So, En becomes ENO, Nt becomes NTO, so minus CNO, PTO, NO, that is this equation at equilibrium, and this equation becomes EPO, PTO minus CP, NTO, PO. So, if we were to consider the equilibrium condition, we know that these rates have to be 0, and using that we can develop a relation between ENO and CNO. So, we are trying to get rid of this variable ENO. We want to just represent all our equations with CNO and CPO. So, for electrons your ENO is nothing but this term here and your EPO is nothing but this term here. So, this is all at equilibrium. Okay. Now, we make a small assumption. Okay. We will say that as we move the semiconductor, so this is my equilibrium condition. So, I had all these parameters N, P, NT, PT. This is my we had this is my equilibrium condition where we had the parameters NO, PO, NTO and PTO, and we moved the semiconductors very gently out of equilibrium to the non-equilibrium condition, and here my parameters became N, P, NT and PT. Now, we will say that yes, these 4 parameters are different, but the rates or the proportionality constants are not changing too much. So, we are going to make that assumption. Okay. So, we will say that and in the non-equilibrium condition the proportionality constants that relates these rates have not changed too much. Okay. So, therefore, En is the same as ENO, Cn is the same as CNO, EP is the same as EPO and CP is the same as CPO. But although the proportionality constants are being assumed to be the same, we are not assuming that NP, NT and PT are have not changed, because that is a bad assumption. Okay. Because then there is no difference between non-equilibrium and equilibrium condition. So, Yes, NP, NT and PT have changed from their equilibrium positions, have changed from their equilibrium values, but the rates, the proportionality rates that dictate electron hole capture and electron and hole emission have not changed. Therefore, if you make that assumption, based on this connection or this relation between the emission rates and the capture rates, we can say that En can be written as Cn times this little parameter here, and Ep can be written as Cp times this parameter here. Okay, so essentially what we have done is say that En is equal to Eno and Cn is equal to Cno. Now, if we make this, if we take advantage of this assumption, the differential equations that we had for electron and hole change for through RG mechanisms is now given by these two terms, which is now simplified to writing everything in terms of the capture rates. So, we write En in terms of Cn and Ep in terms of Cp and say that these differential equations are now essentially the same as these two terms here. Okay. And we call this very important equation, we give it a label and call it equation 1. Okay. So, now let us just go back to the big picture. Okay. So, this is the total change in electron and hole count in our volume of interest, and this is the change in electron and hole count due to RG mechanisms, and that is what we have been discussing so far. Now, at equilibrium these parameters were both equal to 0, but at steady state these two need not be at non equilibrium these two parameters need not be equal to 0. However, at steady state condition, so we are now out of equilibrium, but we have established a steady state condition. So, what does that mean? So, let me just give you an example in terms of electrical circuits. So, let us say you have a say a resistor capacitor circuit, say something of something like this, and you have a voltage source that is driving a current through this resistor and capacitor. Equilibrium condition means that this voltage source is 0, which means there is no voltage, there is no current through the circuits, everything is balanced out. In fact, there is a lot of movement of electrons inside your resistor. You can see all the electrons moving in both directions, but the movement, the flux is so well balanced out that there are no currents in any of these elements. So, that is the equilibrium condition. So, what non-equilibrium implies is I have now applied a voltage. Okay, so, let us say I have applied 1 volt. Now, the moment I apply 1 volt, because there is a certain time constant to the circuit, it is going to take some time for all these voltages at all these nodes to establish. So, you will see some dynamics there. Okay. So, that is the non-equilibrium transient state. Okay. Everything is moving with time. So, all these voltages are all shifting with time, they are all changing, the currents are all changing with time. And then after some time these transients will all die out and the system will achieve something called a steady state. So, these voltages would now have settled, or there would be very little variation. In fact, ideally there would be let us say 0 variation in steady state. Okay. So, in steady state these transients would all die out and you will have no variation, and you will establish a fixed current, a time invariant current through the circuit, and so on and so forth. Okay. So, this condition is called as being in non-equilibrium, but being in steady state. and whereas this condition is called being in non-equilibrium but in transient. Okay. So, that is the best analogy I can give to this process to what we are looking at. So, in non-equilibrium these rates need not be 0, okay, they are not 0, and in the non-equilibrium transient condition all these parameters need not be 0, but at steady state and non-equilibrium these total effective variations in n and p have to be equal to 0, whereas these individual rates need not be 0. Okay. So, now let us consider the case where we are at non-equilibrium, we are looking at RG mechanisms, we are at non-equilibrium and we are at steady state. Okay. So, which means that these parameters are not 0, but there should be something within the perspective of the RG process that has achieved steady state condition, and that is basically your count of say the trap states that are occupied or the count of the trap states that are unoccupied. So, these could be assumed to be fixed, they are time invariant at steady state within the study of your RG mechanisms. So, therefore, with the RG processes alone we can say that both dN by dt and dP by dt are not 0 individually when at non-equilibrium steady state, but due to the fact that it is steady state this is balanced out by any changes in the whole concentration, and therefore, dN by dt is equal to dP by dt in non-equilibrium steady state condition. So, we will now take this general equation which we have labeled as equation 1, okay, and try to look at the steady state implications on this equation, and the steady state implications are that this rate must be equal to this rate. Okay. So, using equation 1 and establishing this condition we can now solve the equation and estimate what NT is. So, that is the number of occupied states, it is just a bit of algebra that is wherein you equate these two terms, and using that value of NT we can also get PT, okay, because we know NT we can calculate PT as NT minus capital NT minus small nt, which is your small PT, and using NT and PT and in plugging it into any one of these equations, okay, into any one of these we can get the recombination rate, which is basically your dN by dt, the rate at which we are losing electrons, the rate at which we are losing holes. So, we can calculate our recombination rate. Okay. So, in steady state we find that the recombination rate is given by this equation here, and this is a very useful equation, we will give it a special label and call it equation 2. So, what it tells you is that the rate at which the carriers, any free carriers recombine. So, which means what? Which means at equilibrium I had some carriers, I had some electrons and I had some holes. Now, when I took it out of equilibrium in the non-equilibrium condition I added some more electrons. Okay. So, these have suddenly appeared into the material and we have added some more holes. So, this is in non-equilibrium condition, and with time these, if the non-equilibrium condition is not forced, if it is not maintained, if the semiconductor is simply taken out of equilibrium and left alone, it will try to find its way back to equilibrium. Okay. And the rate at which these carriers would recombine, okay, would be given by this rate here. Okay. So, if there are no more mechanisms to generate carriers and there is no other process to take it, keep it in non-equilibrium condition, the semiconductor will head back to equilibrium, and it will head back to equilibrium by sort of annihilating these carriers, these excess carriers, because this is the equilibrium carrier concentration. Okay. So, in order to get for the semiconductor to get back to equilibrium, these carriers will have to recombine, these excess carriers will have to recombine, and that rate can be calculated by calculating this recombination rate. Okay. Although we will be looking at a more general case wherein there is no necessity for the semiconductor to stop being forced in non-equilibrium. So, this is just an example that I am stating here. All right. So, in this equation what do we see? We see that Ni is the intrinsic carrier concentration, okay, which is, so Ni square is nothing but your NO-PO, because your NO was your equilibrium electron concentration, PO is the equilibrium hole concentration, and NO-PO is Ni square. N and P are the non-equilibrium electron and hole concentrations, it is a product of the non-equilibrium electron and hole concentration, and NP is not equal to Ni square because we are in non-equilibrium condition, and this rate depends upon how much we have shifted away from the mass action law. So, if we were in equilibrium, NP would have been equal to NO-PO, and NO-PO minus Ni square would have been 0, or this numerator would have been 0, and there is no need for any recombination rate. On the other hand, if you are in non-equilibrium, NP is not equal to Ni square, and that difference, that deviation from Ni square is what is determining the recombination rate. The next 2 points are, look at these two terms. So, capital NT is the total number of trap states per unit volume, which is related to our RG centers, and these CPs are the capture coefficients for, I am sorry, the proportionality constants for the capture of holes and the capture of electrons, and this term 1 by Cp NT has got a very special significance. Okay, it is given a symbol tau p, okay, and it is called the minority carrier lifetime of holes. What does that mean? It means that if you take a semiconductor that is doped, okay, so let us say a semiconductor is n doped, so it is an n type semiconductor. So, if it is an n type semiconductor, you have a large number of electrons and a small number of holes, okay, the whole population is Ni square by n in equilibrium. Now, you add some excess, you take the semiconductor out of equilibrium and you add some excess holes inside the semiconductor. Okay. Now, there are many electrons and you have just injected some extra holes inside the semiconductor, you have shifted the semiconductor out of equilibrium. Now, the typical time, a measure of the time these holes would last in this n type semiconductor is the minority carrier lifetime of holes. Why minority carrier? Because in an n type semiconductor the holes are the minority, they are the minority carriers, and the electrons are in majority, they are the majority carriers. So, when I inject holes into an n type semiconductor, they would last for typically tau p seconds before they recombine. So, that is their lifetime. Similarly, if we inject electrons into a p type semiconductor, so in a p type semiconductor holes are the majority carriers, electrons are the minority carriers. If we inject electrons into a p type semiconductor, then they would last for a lifetime of about tau n seconds before they recombine. So, that is called as the minority carrier lifetime of electrons. So, it is important that we are not interested in the lifetime of holes in a p type material, okay. So, that is not the minority carrier lifetime. We are interested in the lifetime of holes in an n type material and the lifetime of electrons in a p type material. So, we will now replace these two terms with tau p and tau n. But before that, let us take a look at what these two terms are. Okay. So, what are that? What are those terms? What are PTO NO by NTO and NTO PO by PTO? Okay. So, we will get a good gauge on this. So, PTO NO by NTO are all equilibrium values, they all got the subscript O around it. Okay. But PTO is the number of trap states per unit volume that was empty. Okay. So, this is PTO, and therefore, PTO is nothing but capital NT minus NTO. It is a total number minus those that are filled, and you just divide NTO here and you end up with this expression. So, this expression is the same as that. Now, let us take the reciprocal of this term, okay, which is NTO by capital NT. What is NTO by capital NT? So, you have the trap states here, you have some of them that are filled with electrons, and this concentration is NTO at equilibrium, okay, and this total number is capital NT. So, what is NTO by NT? It is the probability that the states at ET are filled with electrons, okay, it is a measure of that probability, which basically implies that we are talking about the Fermi function, right. So, Fermi function is the probability, gives you the probability that the energy states at energy level E are occupied by electrons. So, f of E, which we discussed earlier, is that probability. So, we are talking about the same case, and we had looked at this condition even in the case of doping, when we looked at the number of donor sites or the dopants that are ionized as compared to the total dopant concentration. So, it is exactly the same argument. So, NTO by NT is essentially the Fermi function with the small correction factor GT, okay. And therefore, this term, which is the reciprocal of this Fermi function. So, you take the reciprocal of this, which is 1 plus GT to the power ET minus EF by KT minus 1, is essentially this. So, this term here is that term within the brackets, and NO is the equilibrium hole concentration, which is nothing but Ni e to the power EF minus EI by KT. So, the product of these two will result in the EF disappearing, okay. So, PTO NO by NTO is nothing but this term, and this product is nothing but GT e to the power ET minus EI by KT. Now, if these trap locations are close to mid gap, okay, so we have not said anything about where ET is. So, if that is EC, that is EV, and let us say this is my intrinsic Fermi level position. If ET, if these traps, the RG centers, are all located close to mid gap, so let us say ET is approaching EI, EI is slightly off mid gap by a factor of KT by 2 logarithm of the NV and NC ratio, and if ET approaches EI, ET minus EI will approach 0. So, this term will become 0, and this GT can nicely be approximated as 1, okay. So, GT will take a value of 1. So, therefore, in the condition that ET lies in the mid gap area, we can safely say that GT is 1, okay, and therefore, the exponent disappears because ET minus EI is 0, GT disappears, and therefore, this entire term is approximately Ni, okay. So, that is the order of magnitude of that term. So, that term is approximately equal to 1 E10 per cc, and similarly NTO PO by PTO by same arguments, okay, can be shown to be approximately Ni if EI is approximately close to ET. So, we now got some simplified results to plug into this big recombination rate expression here. Okay. So, we know that this is, we have given this a separate symbol tau p and tau n, and we know that these two are approximately Ni provided Et lies close to Ei, and therefore, we can write a much simpler expression for R, which is Np minus Ni square by tau p into n plus Ni plus tau n into p plus Ni, and we call this as equation 3, and it is something that is extremely useful in making a quick computation. So, what this expression tells you is it gives you a gauge on the recombination rate, that is the rate at which the electrons and holes are being annihilated, okay, in non-equilibrium. Okay. So, N and P are non-equilibrium values. We have taken the semiconductor out of equilibrium. What is the rate at which the N and P are being annihilated or are recombining? So, that is what R is. So, let us solve a few examples. So, we will make use of equation 3 and let us solve a few examples. So, we will take two conditions, okay, two special cases, because these are going to be useful to us later down the road, and we can simply refer back to these arguments. So, the first special case is something called as low level injection. So, we are in non-equilibrium, okay, and we are in steady state, and we have a condition called as low level injection. So, what does low level injection mean? It means that the excess carriers added. So, let us say NO and PO are the equilibrium values of the electrons and holes, and in non-equilibrium we have added a small number of electrons and a small number of holes, delta N and delta P. And the key to low level injection is that these values are really small. So, what do you mean by small? So, firstly delta N is to the order of delta P, okay, and delta N delta P is less than the majority carriers, is much smaller than the majority carriers in a semiconductor. So, delta N delta P is much smaller than NO in N type semiconductors, and delta N delta P is much smaller than PO in P type semiconductors. Again, sorry, another typo here, it is in P type semiconductors. Okay, so, just to give you some numbers, okay, so let us say let us say we have silicon. So, Ni is 1E10 per cc, and we dope the silicon with donor dopants of 1E15 per cc, which means that the doped semiconductor at equilibrium will have let us say it is purely extrinsic, which means all the dopants are ionized, which so in equilibrium my NO will be close to Nd, which is approximately 1E15 per cc. My PO is Ni square by NO, which is approximately 1E5 per cc, and my delta N and delta P are, let us say, about 1E8 per cc. So, 1E8 is definitely much smaller than 1E15, and these arguments could be applied to that condition. Note that 1E8 need not be smaller than 1E5, that is, we are not talking about, we are not comparing the low level injection to the minority carriers, we are comparing it to the majority carriers. So, that is the only condition we need. So, that is what we mean by low level injection. So, now under these conditions, let us go ahead and use our equation 3. So, just for the sake of clarity, I will write it down again. It said that R is equal to Np minus Ni square by tau p into N plus Ni plus tau N into P plus Ni. So, that was equation 3. So, now what is my N? N is nothing but N, the equilibrium value plus delta N, and P is nothing but P naught plus delta P. So, we plug in those values for N and P everywhere and we open out this term. Okay. So, what happens when we open out this term? Okay. So, you will end up with NOPO, the numerator will be NOPO plus delta N PO plus delta P NO plus delta N delta P minus Ni square, the whole divided by tau P into NO plus delta N plus Ni plus tau P tau N into PO plus delta P plus Ni. Now, NOPO is nothing but Ni square. So, this is Ni square and these two terms can cancel. Now, between these three terms since delta N and delta P are much smaller than NO and since my NO is much greater than PO in an N type semiconductor. So, let us say we are looking at N type semiconductors now. So, in an N type semiconductor this term dominates, okay, and the other terms are all negligible and the numerator will simply be delta P NO. And in the denominator NO is going to be much greater than Ni, it is going to be much greater than delta N, it is going to be much greater than PO, it is going to be much greater than delta P, and therefore, only this term dominates in the denominator. And therefore, my recombination rate for low level injection at steady state for an N type material is going to be the excess minority carriers injected divided by the minority carrier lifetime. So, in this case it is going to be the excess holes injected divided by the minority carrier lifetime of holes. Similarly, in the case of P type semiconductor, so if we retain these expressions, PO is much greater than NO and delta NP. So, these two terms disappear and the numerator becomes delta P, I am sorry, delta N into PO, and from the same arguments this term is what dominates and your denominator will be tau N PO and the recombination rate is delta N by tau N, that is the excess electrons injected in the P type material divided by the minority carrier lifetime of electrons. So, the second example and the final example we will look at is the steady state, trying to calculate the recombination rate in steady state in a depletion region. So, we have not yet discussed what a depletion region is, we will do so very quickly, but a depletion region in a semiconductor is essentially a region in a semiconductor which is sort of engineered to have very little free carriers. So, that the N and P count is going to be extremely low, it is depleted of free carriers. So, which basically means that N is much less than Ni, P is much less than Ni. So, if you use these two conditions in this equation, your NP is going to be much less than Ni square. So, the numerator is simply Ni square. Your denominator, the N is not important compared to Ni. So, here this is a typo again, this should have been P, but that is not important compared to Ni. And therefore, you end up with the recombination rate being minus Ni by tau N plus tau P, and this negative sign tells you that the recombination rate is negative, which means you are actually having generation. Okay. So, in a depletion region there is carriers are being generated, there is an encouragement towards generating carriers, and that generation rate is Ni by tau n plus tau p.